Chalava? Okay, good morning students, and now we are going to see about Maxwell's third equation, which is derived from Gauss law for electric field. We know that psi is equal to Q. Electric flux enclosed by the closed path is equal to the total charge enclosed by the surface. This is Gauss law for electric field. And now I am going to substitute, instead of psi, I am going to substitute this. Because we know that D is what? Electric flux density. How I have already told you, electric flux density is equal to electric flux plus surface. So electric flux is d psi divided by ds. I am in need of psi. So I am going to keep this here. I am going to cross multiply with d. So d psi is equal to d dot ds. And afterwards I am going to take out the differentiation by taking integration on both sides. So d and differentiation, integration get cancelled. Psi is equal to integration of d dot ds. I am going to substitute this value instead of psi here. So see, instead of writing psi, I have denoted integration of d dot ds is equal to. So instead of q, you want to substitute an integral form. Okay. So q is what? Charge. We already know that volume charge density rho v is equal to what? Charge per volume. Flux density is equal to flux per surface. Charge density, we are having several categories: line charge density, surface charge density, volume charge density. So here I am considering volume charge density rho v. Rho v is equal to what? Charge per volume, dq by dv. So I am in need of q because I want to substitute here. Instead of q, I want to substitute an integral value. So what I am doing here is I am going to cross multiply this with rho v. So rho v dv is equal to dq. See here, dq is equal to, multiply this with rho v dv. Instead of taking, I am going to cancel this integration and differentiation here. Okay, so both are get cancelled, and q is equal to dv means volume integration. So I am here also I am putting in the subscript v. So rho v dv. So instead of writing q, I can replace it with what? Integration of rho v dv. So see here, q, instead of q I am writing integration of rho v dv. So both sides we are having integration. So this is integral form of Maxwell's third equation, which is same for static field as well time varying field or dynamic field. Okay, because here there is no time varying element. T element is not there here in this equation. So this is same for static field as well as dynamic field. So this is Maxwell's third equation, integral form. We want to convert this integral form into point form. So for that, what we want to do is, I want to use the divergence theorem. Divergence theorem is used to convert surface integration into volume integration. So what I am going to take here is surface integration of a vector is equal to divergence means what? We want to take del dot. This term represents divergence of volume integral of the same vector. Here d vector means here also you want to take d vector. So this is divergence theorem. So now equate these two equations. Left hand side we are having surface integration, and I can able to relate these right hand side. So I am considering the right hand side of these two equations. Integration of rho v dv is equal to integration of del dot d dv. Now I can able to cancel the integration because both sides we are having only volume integration. So the inner content is same. Okay, here also volume integration, here also volume integration. So take the inner content rho v is equal to del dot d. Leave the integration as well dv. So rho v is equal to del dot d. So this is point form. Because why I am saying this is point form or differential form? Del, the value of del is nothing but dou by dou t. Dou is nothing but differentiation. So this is point form of Maxwell's third equation, and this one is integral form of Maxwell's third equation. And now we are going to see Maxwell's fourth equation. It is also very simple, which is derived from Gauss law for magnetic field. Third Maxwell equation derived from Gauss law for electric field. Fourth Maxwell equation is derived from Gauss law for magnetic field. It states that magnetic flux cannot reside in a closed surface due to the non-existence of the single magnetic pole. See, you know, one thing, if I am having a magnet which consists of north pole and south pole, if you are going to cut this magnet, means again that the particular magnet consists of both north pole and south pole. The existence of single pole is not at all possible. Okay, so this statement states that only. So integration of b vector dot ds vector is equal to 0. See here, I am taking electric flux density. Integration of d vector dot ds vector is equal to psi is equal to q. Q instead of q we have written this. But in Maxwell's fourth equation, we are going to consider Gauss law for magnetic field. Magnetic field means magnetic flux density. B vector you want to consider. So integration of B vector dot ds vector is equal to 0. In a closed path, it is not possible to have magnetic existence of the magnetic flux is not at all possible. So see here, this is integral form of Maxwell's fourth equation. Very, very simple. And again, to have the point form, I am going to take divergence theorem. Divergence theorem that converts surface integration into volume integration. Surface integration of a vector is equal to volume integration of divergence of the same vector. Here B vector means here also you want to use B vector is equal to 0. So this value is 0, I know. So equating this one to 0 means the inner content del dot B vector is also 0. So this is point form or differential form of Maxwell's fourth equation, and this one is integral form of Maxwell's fourth equation. That's all. Thank you.